Let people trickle in here a little bit more before I get moving, like a minute or so. Feel free to ask any questions you've got now. If you've got anything before I get moving, lecture shouldn't run overtime or anything.
Hey, Chuck. So I sent you a question over Slack earlier about producing multiple tables with that knitter function. And I tried it, and I think, so one of the issues I ran into was that the variable that I'm running it over isn't that original variable that had like numeric values for month, but it's
right.
categorical. How do I deal with that?
Here's an example, something like that. Let's say that I want to do one plot for each level of cylinder in the MT cars data set. I'm going to say take a function of x. Actually, it's kind of clear, make it a function of cylinder. And then say, let's just do, probably have to load. Do cable on MT cars. I guess I can do it this way. That should result. Let's see, cable that. Oh, yeah. So that basically produced two tables or three tables as an output because there's three levels of cylinder, right? So table 1, table 2, table 3. That will look a little bit weird if I probably knit it in a document, but that would programmatically generate three tables. Another way to do it, of course, and technically this is one of the rare cases of things that might operate better in a loop. You could easily run a loop on this instead and just say for like, right, oh, what did I do here? For cylinder in unique cable cylinders. What am I missing here? Should work. Oh, it's populating that variable. that not for cylinder in unique 648 cable? Huh, wonder why that's not printing. Huh, it's not doing it as a side effect. Oh, there we go. Okay, I just had to explicitly print it if it's in a loop. So you could easily do it with a loop like this. One of the nice things with doing it with a loop is it doesn't do the sort of output that lapply does. Lapply and sapply, like it as a default, are going to produce both the printed output and they're going to produce the output as a list. You see how it's in brackets here, and that's probably not what you want.
Right.
So it's easier to do it probably with a loop here.
Okay. Yeah. That's helpful. Thank you.
Yep. Anything else? Okay, and we'll get moving here then. So last week we kind of dipped into sort of more sort of abstract kind of, I shouldn't say abstract, but more applied things with sort of pivoting data and things like that, reading in files. We kind of got away from our sort of foundational stuff that we did in week 4. We're going to zip back to some sort of foundational stuff again. So we're going to come away from sort of the tidyverse stuff, and we're going to come into working with sort of foundational programming concepts. These things we're going to talk about today are, do I have an example? I don't have an outline. We're going to work with loops and flow control right now, which are sort of things that are, well, you can use them in R, are broadly used in just about every programming language you would ever actually write anything in, with the exception of markup languages like Markdown or HTML. Basically, everything out there has loops. The stuff you learned today in this applies to every language that you're going to go out in the future and use. You can always loop them. In R, we tend to do our best to try and avoid writing loops because they kind of suck to write. They're hard to read. They're hard to write. They're a little hard to troubleshoot. But they're very powerful because if you want your computer to do it, a loop can make it happen. Okay. So if you didn't know any better, and when I say if you didn't know any better, I mean, I often have gotten a lot of assignments in other classes written in R that look like this. And you wanted to say get the mean of every variable in the Swiss data set we worked with in the first homework, you might do something like this. You might write one line of code for each column in the data set and pull the means out like this. So you do like mean of Swiss fertility, of agriculture, examination, fertility, Catholic, infant mortality, and then you might bind them all together into some sort of vector to display all the means of these different variables, okay? Well, if you write lots of code, the more code you write, the more likely it is that you're going to make mistakes while you do it. So if you look at this, some of these lines have very obvious mistakes in them. Some of them have mistakes that would cause errors. The problem here is that there's also some mistakes in here that are hard to see and some that would not generate errors. And so you might not even know you'd made a mistake. Things like that include, we've done the mean of Swiss fertility and assigned it to mean 1, but we've also done it here and assigned it to mean 4. No error is going to result. You're just going to get the same mean for mean 1 and mean 4. You might look at your resulting sort of table and be like, oh, it's interesting these two variables have the same mean, but it doesn't kick an error or something like that, right? Other things we've done here is I have 2 mean 5s, right? Down here in this vector, I'm missing a comma over here. I've accidentally typed man 6 instead of mean. You name it. There's a lot of like errors like this. And if you type as badly as I type most of the time when I'm writing, you would make a lot more mistakes if you write large amounts of code. So your goal should really be to write less code because you make fewer mistakes and you're also writing less stuff. Now, imagine if you were trying to calculate the mean for a data set with a lot more columns. How upset would you be if this was the only way you knew to calculate the mean of columns, but you had 200 columns instead of 6 columns to calculate, right? So this scales in a very linear fashion. If I want 200 means, I have to take this and repeat what I have here enough times to get all the way up to 200. You'd have a massive script as a result of that just to calculate some means.
This is kind of dumb, and it sort of doesn't take advantage of the most basic thing computers are good at, which is performing repetitive tasks for you so you don't have to do them. Okay. So a better way to do this would be some solution that takes advantage of the ability of a computer to do a repetitive thing for you so you don't have to. So what we're going to focus on today are what I call general solutions to repetition. How can we make the computer do whatever we want repeatedly over and over again? Okay. Next week, we're going to talk about better methods than what I show today, but they tend to be more specific to things or involve a little bit more of a technical understanding of some things. So what we're going to talk about today are loops. And a loop looks something like this. I'm not going to go in detail about what this is doing because we're going to walk through how these things operate extensively today. But the gist of what this is doing is we're creating an empty vector called Swiss means that I'm going to assign a bunch of values to. And then I'm saying, what I want you to do is for some value in a sequence along the Swiss data set, I want you to assign to each value of Swiss means the mean of the Swiss data set for a given column. So this loop here, we're going to walk through the stuff. It's okay to not understand what this is. If I say Swiss means now, what's happened is it has correctly assigned all the mean values for every one of these columns. Okay. Well, the nice thing about this code, well, first I'll say the bad thing about this code. The bad thing about this code is if you haven't written a loop before, you're going to look at this and be like, I don't want to write loops because this looks terrible, right? There's all sorts of brackets and squiggly lines and things. It looks like, you know, what we imagine computer programming looks like when we're writing in things not the tidyverse, okay? But the nice thing about this code is if Swiss instead had 5,000 columns, I would not have to change a single letter of this code. It would properly generate the mean for all 5,000 columns in it, assign it to the vector and display it. This is code that scales nicely because no matter how large the Swiss data set is, this code works exactly the same. This is sort of the ideal thing you want when you want repetitive code. Something that doesn't care about its input too much. It just works and generates what you want. You run it once, it'll work for everything. So a question here in chat is, so a loop isn't the only way to solve this problem, is it? No, we're just learning this as using this issue to learn loops. Yeah, so actually, if you really wanted to do this exact same thing here, this would be much better done with a apply statement, which I'm going to show you in a bit. And because he asked, I would instead do this with that, and it would give me a vector of the means of the Swiss data set. Could convert this over to a proper vector like that, say sapply Swiss mean. This is way easier than the loop, and this is what I'm going to focus on next week, but this requires some mastery to understand what's going on. The thing that a lot of R people will not tell you is that lapply and sapply actually are loops. They just don't look like them. So we're going to learn the foundational technique of writing a loop manually before we get to iterative things using the apply family like this. But this is the way you're going to want to do it in the future. Okay. But you need to learn this foundational loop stuff because it's very powerful. If you want to do something on your computer, a loop can do it. Because honestly, everything currently running on your computer, your phone, every electronic device you own is actually a loop. Loops are sort of the foundation of all operating like digital devices. If you know how to master loops, you can theoretically go to another language and write literally anything you want to do, right? It's all loops all the way down. Okay, so loops are very powerful. They suck to learn them. So I've kind of iterated over this lecture many times, and I think this is a pretty good introduction to it, at least hopefully not completely traumatic. But we'll see. Okay. So the idea for today, and is a general idea to apply to all of your programming, is this concept called dry. Don't repeat yourself. The idea is that computers are way better at doing things over and over again than we are. So anytime you need to do something over and over again, make the computer do it. What qualifies as over and over again? If I'm going to do anything more than twice, I write a loop or some other iterative thing to do it. I'm okay doing something once or twice. At 3 times, I write a function or something like that. Okay. That's actually a good one. We're all strange loops all the way down. We're all repetitive behaviors nested. So Writing code that repeats tasks for us will reduce or remove most common human coding mistakes. These are things like if you wrote 500 lines of code and there's a typo in there, you may never be able to find it because it's sort of buried in all this text. The less text there is, the easier it is to find mistakes. Okay. Another thing is that it will substantially reduce time and effort you spend processing large volumes of data. What qualifies as a large volume of data for this is really small. Even working with a data set with 12, 20, something like that columns is much easier using statements like this than manually doing them all. And probably every real data set you're going to work with, unless you run like clinical trials, actual experimental clinical trials, it's probably going to have a lot of variables you need to work with. So you're going to want to learn how to do repetitive things. If you work with nothing but crosstabs like binary inputs and outputs, it's strange that you're in this class to begin with. But if you do nothing but that sort of thing, don't really need anything. You can do it manually. Anyway, compact code, as I kind of mentioned before, it's easier to read. It's easier to troubleshoot. And part of the reason it's easier to troubleshoot is if you make a mistake, it will probably kick an error message. When you make a mistake in lots of handwritten, repetitive tons of code, often those mistakes are the type that don't kick error messages and you just can't find it because it's buried in tons of code. If you have scripts that are like 500 lines of code, you're probably doing something wrong. You need to trim that back. Okay. This is one of those things where you often have people who are novice programmers, new people who will like brag on Twitter to be like, I wrote 1,000 lines of code to do this thing. If you were in an actual programming job and you wrote 1,000 lines of code to do anything, you'll probably get fired. Okay. So you don't want to be writing lots and lots of code. It's a nightmare. Professional, hardcore computer programmers spend lots and lots of time writing very little code because it's about compactly doing things in a modular way that's highly easy to troubleshoot. Okay, this is a functional programming type thing we'll kind of get into later. Tiny code, don't go over the top. If you know how to do something in like 25 lines of code, don't stress about reducing it to 10 or 15. That's fine. But if you've done something in 500 lines of code and you're pretty sure there's a way to do it in 25, there might be a good reason to trim it down. I've taken scripts that I wrote maybe in the second year I was using R. I actually just did one that was about I think it was 650 lines of code to process some data from some complicated field experiments we ran back then. I rewrote it for the purpose of getting this paper ready for being sent out to a journal, and I trimmed that 650 lines of code down to 17. And it was just like, oh, I know how to write good code now. And I'll tell you what, I can troubleshoot a 17-line crisp little piece of code like that a lot better than that 650-line monstrosity, proven by the fact that I found multiple coding mistakes in that kind of messed up some of my results in the original draft. Compact code, easier to find. I'm saying functional lines. Doesn't include blank lines, but in this case, it had no blank lines. It's a single pipe chain. But very often it's the case that, if somebody wrote like 50 lines of code, they probably mean 50 lines of code plus like 30 lines of documentation written into it and stuff like that. I wouldn't consider usually the comments to be code. Okay, so the agenda for today is focusing on fundamental programming concepts. So we're going to talk about for and while loops, the two most commonly used loops in R. Mostly for loops are the most common. And then I'm going to talk about vectorization to avoid writing loops. So in the first lecture I introduce loops, I will promptly introduce avoiding loops, just to let you know you usually don't want to solve a problem with a loop, but if you can't solve it any other way, a loop can definitely do it. Okay. Next week, we're going to get into writing your own functions, which is a really powerful way to sort of accomplish things. Every function you use in R, things like select and filter, minimum, you name it, those are all functions somebody wrote, and you can write functions the exact same way they wrote those, and we're going to next week. And then I'm going to talk about how to use looping methods based on functions and iterative methods based on functions using apply stuff. Okay. So what is a loop? I keep saying loop over and over again. You're going to get tired of hearing me say loop. So I actually really like Wikipedia's definition of a loop, so I'm just going to read it. Okay. A loop is a sequence of statements which is specified once, but which may be carried out several times in succession. The code inside the loop is obeyed a specified number of times or once for each of a collection of items, or until some condition is met, or indefinitely. And that is a basically fully comprehensive definition of a loop. That's what a loop is in its abstract terms. Okay, so I'm going to talk about for loops first. For loops are the most common loop you would encounter sort of in a data science or stats setting, but not necessarily the most common loop for like general programming, which might be a while loop or just a sort of perpetually repeating loop. Okay, so for loops are the most general kind of loop, at least in data programming. They're found in every programming language that's like Turing complete out there. I don't know of any commonly used programming language that lacks a for loop, except for markup languages like Markdown and HTML. You can write loops in Stata. You can write loops in SPSS, you name it. Everything will do a for loop. So a for loop is just this. For each of these values, in order, do this thing. So anytime you see a for loop, imagine that's what it's saying. For some set of values, do these things to every one of those values. So they work like this. You begin with some set of values. So given a set of values, let's say it's the numbers 1 through 10, right? You will set an index variable, maybe some variable like I, equal to the first value of this set we have. You'll do some set of things that usually depend on the current value I. After you're done doing those things, you check and see if there is a next value. If there is a next value, update that value to the new one, go back and redo 2, and keep doing this until you run out of next values. If you're out of values, you stop looping, okay? The idea is that you are looping through values to repeat some action. Graphically, a loop looks like this, and the reason it's called a loop is you can think about it like this. It actually draws sort of a loop graphically. Given some set of values, let's say we're going to iterate over the variable I. So given some set of values, let's set I to be the first value of that set of values. We then run some code using I. Once we're done running that code, we check to see if there are more values of I. If there are, yes, we set I to the next value, run the code again using I. We repeat this, thus the loop, until we run out of values to fill I with. Once there are no longer any more values, we exit the loop and it finishes running, okay? This might be iterating over every like element of a vector, like a bunch of numbers in a vector, but it might also be iterating over columns in a data set, rows in a data set. We might be iterating over multiple data sets in a list or something. You can iterate over anything you want, but the idea is that you're going to basically replace I with values over and over again until you run out of them. Okay. So here's an example of a simple for loop in R. I'm going to say for I in 1 to 10, I want you to print I squared. So what this says here is we're going to do a for loop. The variable we're going to change every time the loop runs is I. So for I, this is what we're going to iterate over in the values 1 to 10. 1:10 is the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So all this loop is going to do, what this statement right here says, is I want you to do whatever is in the brackets. 1 second, I've been visited by a cat. You are very loud. Go on, go on. Okay, thank you. Oh, dangerous cats. Okay, so what this is saying is that repeat the code in these squiggly brackets here 1 time for every value of 1 through 10. This means all the code in here is going to run exactly 10 times, and all it's going to do is take I and 1 by 1 replace it with each value of 1 to 10. So I is going to get replaced with 1. It's going to be squared, and it's going to print it. You're going to get 1. 1 squared is 1. 2 squared is 4. 3 is 9. 4 is 16. 5 is 25. So this code, because there's 10 items here, 1 through 10, it just prints 10 things, one after another. Okay? So this is running 10 separate print commands. That's all the loop does. It runs something once for every value that you're looping in. Does that make sense? Any questions about that? So to illustrate this, the left is a loop doing the same thing, running only from numbers 1 through 3. It says for I in 1 to 3, print I squared, which gives me 1, 4, and 9. What the loop is actually doing, what it is literally exactly doing, is the code on the right. It first sets I to be the value 1, because that's the first value over here. It does the print command in here. It then updates I to the next value, runs print, updates I to the next value, and runs print. Meaning this code here gives you this result. This code here gives you the exact same result. These look the same because they are doing exactly the same thing. The code that's running on the left is identical to the code running on the right. The only difference is we've used this for loop to do these assignments for us. It does the assignment and then runs the code in it. Okay? Does that make sense? Loops aren't too scary when you look at them like this. They start to get very scary when you do things like put one loop inside another loop inside another loop, and you're iterating over lots of different things, which I'm going to show you in a minute. But right now, this is pretty simple. It's just saying, I want you to run this code inside the squiggly brackets until you run out of values up here. And you can put anything you want up here, and it will just iterate through them. Okay. So, iteration conventions. We call whatever happens in the loop for any one value an iteration. So when you hear me say an iteration of something, that just means we did everything in the loop once. It's very common to iterate over indices like 1 through n. Say we're going to loop for I in 1 to 100, which will give us 100 iterations. N, that is the maximum iteration, might be the length of a vector, the number of rows or columns in a matrix or data frame, or the length of a list. We might be iterating over some object like that. Common notation you'll see in most programming languages is I will be the object that holds the current value in the loop. It's most of the time, most languages, people sort of default to saying for I in some set of values. This is just common convention. You don't have to do that. If you have loops inside of other loops, it's quite common that people will iterate over I and J and K. So you'll see single like letter value variables, and they'll just go say, I'm iterating for I in J in K. Okay. So this notation, you might notice, is quite similar to the notation for indexing in mathematical operations. So if you see a summation operator like this in a stats class or something, this says, I want to sum over some values. The values are I, beginning at the first value I until we get to the nth value of I. Okay? So this is actually a sort of a loop saying, I want you to sum for I in 1 to n. Okay? So the thing about this is if you see literally any mathematical operator that looks like that, a summation operator, the product sum, any of those that has like an I, a J, K, N, you can write a loop in R or any language to do exactly the same thing. These mathematically are loop operators. Okay? If you summate like that, you can do it with a loop in R by just copying this into R syntax. Okay. In R, normally we just use a sum function, but you could absolutely just write a loop to do this. Okay, so something to note is that the things you iterate over like I and J and K are normal objects in R, which means you can use any names you want. You don't have to use I and J and K. If I'm iterating over the rows of a data frame, instead of iterating over I just iterate over row. I'll name that object row. If I'm iterating over columns, I'll usually name it col or column. You can name them whatever you want for convenience. And to trip you up, I've used a whole bunch of different names to name iterators in through this lecture, so you can see that they change and you're not stuck with any one of them. Okay. So here's an example of something else. We don't necessarily have to iterate over numbers either. We could iterate over any object in R, including a vector of characters, that is a vector of text. Here I'm going to say, I want to pull out some letters. Some letters I'm going to assign to that letters 4 through 6. That is the 4th through 6th letters of the English alphabet, lowercase, that is D, E, and F. And now I write a loop that says, for I in some letters, so remember this is D, E, and F, I want you to print I. Well, it just prints D, and then it prints E, and then it prints F. Okay, so we can iterate over non-numeric things. This is a character vector, and it just prints each one of the letters in that. Okay, the thing in R, unlike in many languages, is when you say for I in something, whatever I here is actually created in your global environment. So if I run I after finishing running the loop, it stays F. This is because the last thing I was when the loop ran was F. So what R is actually really doing is just assigning each value of some letters to I one at a time. When it gets to the end, it just leaves it with the last thing it assigned to it. So I still exists. Okay? Because this object exists outside of the loop, you don't want to write something here you care about. Don't say for C in some letters, because it's going to overwrite your vector creation function C. Don't be like for sum in some letters, because it's going to overwrite the sum function. Okay? So don't put anything here you kind of care about, but I, J, and K are safe. Most other single letters are safe, but not C, okay, or T for that matter. There's a few others that you can't use either, but I can't remember what they are. But they're not reserved. It'll let you do it. Okay. So there's a handy function if you want to, say, iterate along a non-numeric vector, but you actually want like I in your loop to be numbers. There's a function called sequence along. If you say sequence along X, it will produce an integer vector of 1 to length X. So if I have X here is like, let's say it's a length 25 vector, sequence along a length 25 vector will generate the numbers 1 through 25. Okay? It's just a way to generate a sequence of numbers in sequence equal in length to whatever object you give it. Okay? So if you're in a case where you want to loop over something that is itself not numeric or not in order, but you want a numeric index of where you're at in the loop, this is really useful. So for example, I say for A in sequence along some letters, I want to do something. Now notice here I said for A instead of for I. That's because this thing right here is arbitrary. I could say for I can say for A, I could say for some object in sequence along, it's perfectly happy. In this case, it's just going to create an object A and assign to that object each element of sequence along some letters, one after another. Okay, so some letters, if we remember, this vector is the letters D, E, and F. If this is D, E, and F, what is sequence along some letters? What's in that? Yep, I see your hands. It is the numbers 1, 2, and 3. Okay, so what it does is it just creates a sequence of integers running across and up to the length of some letters. So what we're going to run inside our loop is we're going to say, I want to print out the result of this code here. This code is, I want to paste together a bunch of text. That text is going to be letter A, whatever the current iteration is, colon, some letters subset down to the current iteration. So the first time this runs, A is going to be the number 1. So you can imagine we're going to say letter 1, colon space, subset this down to the first element of some letters. So A gets replaced with 1. That happens to be the letter D. printing out letter 1 is D, the second iteration, letter 2 is E, letter 3 is F. If I then run A at the end of all of this, A remains the number 3 because that was the last thing A was in the last iteration of this loop. Okay, so I've stepped up the complexity slightly here. Any questions about this? Nothing so far. Loops tend to be confusing to people, so I don't mind going slowly on things. Loops tend to break the brain a little bit if you find them unintuitive, and then one day suddenly click. So if you're scratching your head right now, that's normal. Don't feel bad about that.
Sorry, can we explain why A equals 3 instead of 1, 2, 3?
So what has happened? This is a great question. So what's happening in the loop is sequence along some letters, right, is 1, 2, and 3. But the way a loop works is it assigns any of the values here one value at a time to A. So the first time the loop runs, it assigns the first value 1 to it. The second time it runs, it assigns 2. The third time it runs, it assigns the number 3. So when it's done, it's just the number 3 instead of being 1, 2, and 3. So it's literally running, I show back here, it's actually running this code here. So it's assigning a single value, in this case to A, then A, and A, but it's only one value at a time.
So the A is the last value we assign to, okay, thank you.
Exactly. So here's actually a great question here. Why do I have paste 0 instead of paste? I'll show you. We're actually going to spend some time on this in the week 8 lecture on string manipulation, but there's basically two commonly used paste functions. If I say paste, and then I say, let's paste together, I guess I can say paste 1, 2, and 3. You'll see I get 1 space 2 space 3. If I say paste 0, paste 0 doesn't put the spaces there. So paste and paste 0 are basically the same function, except paste 0 is actually paste with separator equals nothing. It's a shortcut function to say, I want you to paste some text together, but don't put any spaces there. In other words, it's me being lazy and not wanting to type separator equals nothing. We'll spend a bunch of time with this on week 8. Okay. Next one. So usually when you run a for loop or any kind of loop in R, you don't just want to print the output to the console like I've been doing. Instead, you want to run some kind of calculation, and then for each one of these iterations, store the result of that calculation somewhere. You want to keep the results, okay? So if you want to do that, you need to figure out what it is you want to store from the loop, and you need to create an empty object of the right size to store those values, okay? So the idea is that you need some empty vector. If you want to do 10 calculations that generate numbers, you need like a length 10 empty vector that you can put each one of those results in to store it, okay? So here's a question in chat. Why doesn't this work? For I in sequence along letters 4 through 6, do this. Let's look. Object A not found. The reason for that is A here doesn't work because I've created the object I instead. If I flip this to I, it will work. Oh, now some letters isn't found because I need to also say some letters. I'm going to have to do, actually, I could just take letters 4 through 6 and replace some letters with 4 through 6. Object A, I not found. There we go. Letter 1, D, letter 2, E, letter 3, F. So that right there, how I made like 3 mistakes before I made that loop run, is why I don't like writing loops either, right? Because you have to change all these little things in them to make sure they work. Otherwise, you get little error messages. They're a little finicky. Everything has to be just right, okay? Yeah. By the way, you might notice something real fun in my RStudio window right now. You notice something fun about my parentheses and my square brackets? You notice how they're rainbow colored? So this is a new thing in RStudio 1.4, which they just put a preview out of. It does rainbow brackets and parentheses so that you can always tell which one belongs to which pair. So you can tell that this pink one over here is matched to this one over here because they're the same color on the rainbow. This is a really handy thing if you're working with big nested things. If you want that, go get the preview version of RStudio. You can turn it on in the options. I just did it earlier today and I love it. It was so cool. Okay. Plus you get pretty rainbow, so I'm down on that period. Okay. So anyway, what we need to do if we want to save results from a loop, we need to create empty objects to stuff these results into. So you might have to pre-allocate all sorts of different types of objects. And in R, there's a lot of different ways to generate an empty object to store stuff in. So if you're going to run a loop where each numeric, like each iteration produces a numeric value, you probably want a numeric vector to store stuff in. If you say in R, numeric, and then a given number of iterations, it will create an empty numeric vector with that many observations. So if I say I want to write a loop that has, say, 15 iterations, if I say numeric 15, it will generate a length 15 vector of zeros. Okay? It's an empty one. If I say character 15, it will generate a length 15 empty vector of character data. Okay? So there's shortcut functions like this to generate empty vectors. Okay? There's also logical. Now, if you want more complex things, let's say for every iteration of our loop, it's going to generate an entire numeric vector. Maybe then we need to save it as rows or as columns of a matrix. We might say matrix NA, fill it with NAs. The number of rows in the matrix should be the number of iterations, and the number of columns should be the length of the vectors this loop is going to produce. All right? So here's a question. Is there a way to just tack a value onto the end, something like that? That will exactly work, actually. So that would be the code to do it. Say create Z and then like add something to it. There's a big problem with that, though, is that in R, if you add something, you append something to a vector, it has to rewrite the entire vector. It doesn't actually append it. So that's very, very slow. So the reason we don't want to do that is because of the speed. It will slow your loop down massively, like sometimes an order of magnitude of 50 to 100 times slower than if you pre-allocate and do the slots. This is called, the actual formal term they call it is, it's like growing a vector. It's bad. R is one of the things that makes people think R is a slow language is that R is slow at growing vectors. Some languages are fast at growing vectors, and so you can do that. Languages like C++, super fast at growing vectors, so just do it arbitrarily and it can append. R is tremendously slow at it. And most people who think that R is slow are writing code that's growing things without realizing they're doing it. In reality, R is basically exactly the same speed as Python, faster for some things, but it can be really slow because it doesn't grow things very well. Okay. If you have some complicated object being produced by a loop, like let's say you have a loop where every iteration produces a whole regression model, you probably want to save it right to a list, because lists can take anything you want in each value, which is what we're going to do here in a minute. Run a regression model over and over again and assign it to a list. So here's an example of pre-allocating something and then running sort of some math to fill it up. I'm going to say I want to make a loop that's going to run for 10 iterations. So I'm going to write an object called iters for iterations. I'm going to set it to 10. I'm going to say I'm going to make some vector of output. This is just going to be a numeric vector of length 10, right? Iters is the number 10. So output here is an empty length 10 numeric vector. I then say for I in 1 to the number of iterations, so 1:10 is just 1 through 10. What I want this to do is instead of printing my output like I've been doing before, I'm going to say take the output object, assign to its ith element, So in the first iteration, it's going to assign to its first element. In the 10th, it will assign to its 10th element. Assign to it this math, I minus 1 squared plus I minus 2 squared. There's some math name for this mathematical sequence, but I forget what it is. And then I'm just going to display my output. So what it's done is it's filled each value of the output numeric vector with the result of this mathematical formula. And the idea here is instead of just printing it to the console, it's written it one element at a time to output, and then I display output. Okay? Does that make sense? We pre-allocate a vector, we write results to it, and then we can do what we want with the results. You could imagine instead of this being the output vector, you could have something like data frame $sign output, and it would fill in all of the values in a column in a data frame. Yeah, exactly there. So it says in chat, and you're making it so future updates only need to change iterations. Absolutely. If instead of going, say, 10 iterations, I wanted 500,000 iterations, I could just replace this with a number 500,000, and it would run this 500,000 times. The only thing I'd have to update is this right here. Exactly. This is a general philosophy. You'd make it here so I don't have to update any other part of this code. So I could actually take this right here, and I could write the code here. So you'll see now that I've allocated the vector, it's a length 10 empty vector. I run this loop. I display output. Well, instead of doing 10, I could do 30 iterations. And there's 30 iterations of the same formula. Right? That's all there is to it. So here's a question. Does it make you nervous to fill a vector matrix or whatever with numbers rather than NAs or NANs? Yes, actually. So the default behavior of filling a numeric vector with zeros is kind of weird. So very often I will populate something with NAs instead, but you got to be specific about how that works. So I might instead do this. I might say, let's populate output with repeat NA 10 NAs. Now, watch what this object actually is. If I repeat NA10, it looks NAs like that, but it defaults to a logical because NAs are a logical. So you got a couple options. You could say NA real number, and now it's numeric. Or you could say leave it NAs like this and populate as numeric. And that right there is what I would normally do. But I kind of wanted to show the numeric here. You can also, I think, OK, you actually can't specify that it's anything other than zeros. But yeah, they default to filling it with zeros. I don't know exactly the reason for that, but that's just the way they do it. Yeah. NA would be my normal choice, and most things populate filled with NAs or blanks. OK, any other questions? Cool beans. OK. So there's a handy function for pre-allocating things in R that I'll sometimes use, and I've probably used in lab a couple times. The function setNames. SetNames is nice because it will allow you to create an object and assign names to it in the same line of code, thus doing the all-important job of saving me from writing one line of code. So I might do something like create a set of names I want to use. These are names to use. I'm just going to say paste together iteration letters 1 through 5. So iteration A, B, C, D, and E. I could say I want to create a length 5 numeric vector and then assign names to it to say my names to use, go names of this vector. Or I could be super cool and do it all in one line of code by saying set names, numeric 5 is the object I want to create, and names to use are the names I want to assign to this numeric vector. I assign it to a vector. I get the same result, but it's slightly more compact. This is a numeric vector filled with zeros, but these elements are named iteration A, iteration B, C, D, and E. Names are really nice, and I'll show you in a little bit in the regression thing why it's nice to have named vectors, because you can subset them on names. So the reason I'm showing you set names instead of just always doing it this way is every once in a while you're going to get in a situation where you actually can't do this, but you can do this. And I can't think of a good example offhand, but I've probably encountered the situation like that a couple hundred times in my life. So I know it must be reasonably common. Okay. So now what we're going to do is we're going to run through an extended complex example of using loops to do a real type of task a person might do, say in a stats class, a project, data science type thing, something like that. And what that is we want to run a lot of different regression models of different kinds in a loop and then compare their results. Okay? So this is something you could take to another class and a homework or something like that, instead of running, you know, 5, this example only runs 4 models, I think, but you could easily do it with like 100 different models if you wanted. It'll work perfectly fine. It scales nicely. Okay, so suppose that we got some data we're working with and we want to fit a bunch of different regression models to it, right? We want to know which one of these models fits our data better. So what we want to do is we want to run each one of these models. We want to store the results of fitting the models as elements of a list, because the result of like the LM function in R and all other statistical methods, the results are a list. If you want to store a list in something, you got to store it inside of another list. Okay. So to do this consistently, we would probably want to write a loop. The nice thing with a loop is if we have 2 models, it'll work. If we have 200 models, we could use exactly the same code. Okay? It'll work exactly the same no matter how many models you give it. Loops are nice like this for the scaling. Okay. After we do this, we're going to do something more advanced. We're going to run cross-validation on these regression models to get an estimate of their actual accuracy in predicting out-of-sample values. This is a complex example, so I don't expect people in this class to know anything about regression, and I really don't expect you to know anything about cross-validation. But by showing you how to run multiple models in a loop and then do cross-validation in a loop, if you run into problems where somebody asks you to do cross-validation in the future, you can now steal and modify my code to do it. It gives you a foundation to do it. And this is a common thing you might be asked to do in numerous CSSS classes. I know of 3 different classes that have a cross-validation exercise somewhere in a homework. This code will work for that. And at the same time as giving you tools to do it, I'm teaching you how it works. So I'm not just giving you like a homework shortcut. Okay. So to do this example here, I'm going to simulate some data that has a known relationship so that I know which model is going to fit best. Okay. So here, basically, I'm just saying I'm going to set a seed, like I mentioned earlier in class or lab. Setting a seed, just make sure every time I generate these lecture slides, I get the same result so I don't get something weird. What I want to do is I want to generate a data set that has 300 observations. So I'm going to say N is 300. I'm going to say I want my data to be draws from a random normal distribution, 300 draws with a mean of 5, a standard deviation of 4. This is going to be my X or predictor variable. Then my simulated data is going to be a data frame where X is equal to X, but Y is equal to some formula based on X plus some randomly distributed error. Okay. And so the idea here is that you need a little bit of error in it so your regression models don't perfectly fit the data. Something kind of funny, and I'll get the questions here in chat as soon as I'm done talking. There was a big scandal in political science where a paper got into the journal Science, the highest journal in the land, and got retracted because people discovered that the data were basically obviously fabricated, and they showed that they were almost assuredly fabricated using R's R-norm function or some other exactly equivalent function like in Stata or whatever. And the way they discovered that is that randomly distributed standard normal error does not exist in real life. So if you're going to fabricate your data, do not use a perfect normal distribution because it will be very obvious you fabricated your data. It's one of those things that's sort of a unicorn. It doesn't really exist unless you are working in like astronomy or physics, places that actually have real Gaussian processes at work. Otherwise, you're not going to see it. This was social data. In social data, you definitely are not getting perfectly normal errors. Okay, so questions in chat. I was just playing around and realized I could do numeric iterations divided by 0 and produce a numeric array of NaN. Are the reasons not to do this? No, that'll work perfectly fine. The only reason it won't work exactly fine is in R, not a number doesn't behave as a missing value. It's not a missing value. So if you care about things that like require check for missing values, is.na will return a false for not a number. And so it depends what you want. So, you know, depends what you want. Generally works though. If you want to make sure it's non-numeric, that's a real quick shortcut for it. Question here, what does 98105 mean? 98105 is my current zip code. I just arbitrarily picked this number as a seed. All this says is I want to start R's random number generator using this number as a random seed. What this means is that as long as this number is 98105, my randomly drawn results will always be exactly the same afterwards. Okay. Yeah, I usually just randomly pick a number. Any number works.
Thank you.
Okay. So, got some random data. If I plot these random data I've generated, they look something like this. I'm saying here, make a ggplot of my data, which is sim data. X is X, Y is Y. Throw on a geom point, give it a title, and this is the relationship we see in our data. If you have even relatively minor statistical training, you'll know exactly what type of model probably fits these data best. And if you paid any attention to how I randomly generated it, you'll also know what model fits these data best. But basically, we've got some sort of parabolic relationship in our data, which we're going to fit a bunch of regression models to. Okay? Fitting a straight line to these data is probably not going to produce a good result. So we're going to run through a bunch of different models that draw different curves. Okay. So these are our candidate regression models. Let's say we want to run some statistical models, and we're going to run a few different ones. What we're going to do is we're going to start with the most basic model we could possibly fit, and that is an intercept-only model. We're going to say that the expected value of y conditional on x is equal to some fixed parameter, which doesn't even depend on the data, okay? As in it doesn't vary along x, okay? It's a fixed value. This basically says draw a single horizontal line that best fits the y values. So the parameter we're going to get from this is an intercept. This is just to draw a horizontal line. Intercept-only model is just a flat line. The next model is a standard linear model. This says we're going to draw a line that best fits the values of y as some straight line function of x. This is a y equals mx plus b style slope line formula. So we're going to say the expected value of y given x is equal to some y-intercept plus, or some constant plus some value times x. This is going to give us a slope to our line on x. Then we're going to complicate this. We're going to run a quadratic model. This says draw a quadratic curve. So y given x is b0 plus some sort of straight sloping line plus some quadratic function of x, which is going to make a parabolic line. It's either going to bend upward or bend downward and come back. And finally, we're going to draw a cubic model. Drawing a cubic curve is a complicated model that looks like this: beta 0 plus b1 times x plus b2 times x2 plus b3 times x cubed. Okay, this model is going to draw something that looks kind of like an S curve. It's going to go up and down and back up, or it's going to go down and up and back down. Okay, in real life modeling, most quadratic models you find in data are not real relationships. Most of them are something other than a quadratic, and definitely most cubic relationships are BS. So usually you're just kind of stretching when you get to a cubic model. There are some rare relationships, and they usually have a very obvious reason for them. People who use quadratic and cubic models and don't have a theoretical justification for them are doing the devil's work, and they should stop doing that. You usually need a good justification for why you expect something to go up and then go back down in a sort of symmetrical way. Anyway, so this is not true for the like logarithmic transformations. Logarithmic transformations often make a lot of sense because they turn your models into multiplicative models, and many real things in real life have multiplicative relationships. Anyway, so if we want to run 4 models, what we're going to need to do is we're going to need to pre-allocate a list that has 4 slots for us to put models in. Okay, well, to do that, I want to do a little bit of setup first. So what I want to do is I want to create a named character vector that's going to store the mathematical formulas to fit these models that we're going to use in the LM function, LM being linear model or linear regression. So I'm going to create a vector called models. I'm going to assign to it a vector. This is going to be a character vector. It's going to be filled with a bunch of text. Now, if you write an assignment operation like this, what I'm saying here is I'm going to generate a vector. The things on the left side are the names of the elements of this vector. The things on the right side are the actual elements that are going to be in the vector. So I'm saying here, I want the first element to be y tilde 1. Y tilde 1 is the regression formula for an intercept-only model. X is not on the right side of this formula, so it gives me a flat line. I'm going to name this intercept only. Then I'm going to name linear is going to be y tilde x. Quadratic is going to be y tilde x plus I x squared. This is one of the many ways in R you can write a quadratic model. Then cubic model is just going to be y is dependent on x, x squared, x cubed. If I copy this code here, throw it into my R, run it, this is what it looks like. Is this too small to see, by the way? I boosted up the size, but it might still be too small. Here, I'm going to boost it up slightly more. Okay. 14 might be a little excessive, but here. So the result of this, so this right here, these are the actual values in the vector. The values are like y tilde 1, y tilde x, y tilde x plus I squared. But their names are intercept only, linear, quadratic, and cubic. What this means, if I say, take this model's object, subset it, and give me only linear, it will give me the y tilde x value here. This is nice because it allows me to subset the vector instead of doing numeric subsetting, like saying models 2, which gives me the same thing. I can say, give me the linear model, and it spits it out. So names are really nice. This is exactly the same thing as like subsetting the Swiss data set by $ fertility instead of column 3 or something. Okay. We'll see in the loop why this is really nice. Okay. So the next thing I need to do is I want to pre-allocate a list to store these models here. So here, what does I mean here? Is it the coefficient beta? No, this is actually a really weird R thing. I says basically perform a mathematical operation in here. Don't do what caret usually means in a formula. So basically, don't worry too much about what it is. Just know you can specify mathematical sort of mathematical formulae in here. This is basically saying I want to square x before it goes into the model. I is basically saying perform that operation ahead of time. I is a really weird R function, and so the only places you'd use it. Yeah. You could also write the same formula instead of like, if you want to do cubic, if you want to do a cubic or a poly model, you could also just say like y tilde poly x2 will give you a polynomial, a quadratic. This would give you a cubic. But by default, it will give you orthogonal polynomials, which are a little bit weird. So question, is that true in any character string? Well, it depends. So no, it's specific to formulas, actually. That's a formula-specific thing, I think. So if I do question mark I, it's inhibit interpretation or conversion of objects. So it's an as-is operation, which you specifically would probably only use in formulae, but you could use it in other cases. So for instance, here it's used to inhibit interpretation of operators like plus, minus, star, and that, and use them instead as arithmetic operators. This is the only use case I've ever used it for. It does weird things in other cases. Yeah. Okay. Is I working as a breakout thing? I'm not sure exactly how I would term that, but it's kind of, it's an as-is operator. Not operator, but function. It's a weird thing. Anyway, so what we're going to do now is we're going to pre-allocate a list using this. So I say my fitted linear models are going to go in some list. To create a list in R, a list is a type of vector. So you say, I'm going to create a vector of type list of length equal to the number of models I have. This will give me a length 4 empty list. And then I'm going to assign names to it based on the names of my models. This is going to produce an object that looks like this. It's a list whose first element is named intersect only, because that's the name up here. Linear, because that's the name for the second thing, quadratic, and cubic, right? So I basically took the names of the model object and applied them to my fitted linear models list. I'm actually going to run that in my console, actually in my editor here. Okay, I get the exact same thing. Okay. So we now have this empty list. What we want to do is fill this up with glorious models. So what we're going to do, basically, is we're going to loop over our vector of models. We're going to fit each one of them and store it in the appropriate slot in that list we just created. The formula function is a function in R, which will convert a character string, like the formulas I have in my vector, into a model formula to run it in LM. So the loop we're going to run is this. For the current model in the names of our models, I want to assign to my fitted LM's object in its mod slot. So whatever current model we're on, this named slot of fitted LMs, I want to assign to this a linear model whose formula is, this, remember, is a vector of models. This is going to subset it to the specific model we're working with. And the data is just our sim data we generated before. Okay, so how does this work? If I put this in here, oh, I didn't create my simulation data. Yoink. Okay, so this fitted LM object, if I do structure on it, we're going to get a huge dump of crap. The reason for it is that each element of this giant list, for instance, the last element is $quadratic, is the entire output of a regression model that ran the quadratic model. So it actually should be cubic, should be the last one. There's the cubic one. Okay, it generates a big object. If I say fitted LMs, give me the first element, that is the output from the first regression model. I could say, for instance, summary on this, and we get the conventional regression object that we would expect. I could also subset it by saying intercept only by its name, and I would get the regression model output. Okay? So this is basically run this model one time for each regression model. So the first iteration of this, literally what the loop is doing is it's saying, take the first name in models, which is intercept only, replace mod with intercept only, and that's all it's doing. It's saying, take my fitted LMs object, subset to intercept only, the first element of it, run a linear model with a formula with our first formula, which is just y tilde that. If I run formula on it, it spits it out as a formula object using our sim data. This model right here is just our first linear regression. All the loop is doing is replacing intercept only on both of these things with linear and then quadratic and then cubic and running our model 4 times, which means it's literally exactly the same as me doing 4 lines of that, but replacing this with linear, replacing this with quadratic, and replacing this with cubic. This is what the loop is actually doing. It's just iterating over these names to run our models. Okay. So we fit a whole bunch of models using a simple loop. The nice thing about this, if we actually had 100 models, this loop would look exactly the same, and we can run 100 models. For 4, it's not an obvious gain. We wrote like the same amount of code, but it would save you more later. Okay, so what we actually want, though, is we want to get predictions from these models and see how they compare to the underlying data. So here's a great question. Why are we using fitted LM's double brackets, but not single bracket? The wonders of single and double brackets. The reason for this is we're assigning to the actual like sub element. We want to assign something to that element of the list. If we use single brackets, it's going to expect we're assigning a list to a sub list of that thing. It's kind of hard to explain, but it will break. Double brackets are when you're extracting or assigning a single element of a list and not an entire sub list to that list. You could try it out and see what happens. It might not be pretty. Basically, usually you're going to want to use double brackets with a list. So the next thing we're going to do here is we want to get predicted y values for each value of x in our original data set for each one of our models. So what I'm going to do here is I'm going to create a new data frame of predicted data. These predicted data are just going to be our original simulated data first. Then what I'm going to say is for each model in the names of our models, so for intercept only, quadratic, and all that, what I want to do is I want to make a new column in the predicted data for each one of the model's predictions. So what I'm going to say is in our predicted data, we're going to subset to a column named the current model we're working with. So this is a data frame. Double brackets will subset to a column. If this column named mod, whatever this mod is, for instance, intercept only, linear, or quadratic, if this doesn't exist and we assign to it, it will create that column. So imagine mod for the first iteration is intercept only. We're going to assign to that the result of predict my fitted regression models subset down to the intercept only model, predict using our predicted data. This basically just extracts fitted values from the model, but it runs it once for each one of the models. If I come over here, I'm going to delete all this junk. Create some predicted data. So predicted data right now, here I'll get head on it. Predicted data looks like this. It's a bunch of X's and Y's. What we're going to do is we're going to loop over each of these models. And now predicted data has a predicted value for each value of X for each of our 4 models: intercept only, linear, quadratic, and cubic. So what our loop has done is every iteration of the loop has generated a new column in the data set and filled it with predicted values of Y given these values of X, because that's what the predict function does. Complicated, but it was a quick way to get a bunch of columns. Okay. So this is the data frame we just generated, the same thing we saw in my console over there. What I want to do, though, is I want to plot this on my ggplot. If you remember, ggplot does not like wide data. What I want to do is I want a bunch of lines, but to do that, I don't want to plot intercept only, linear, quadratic, and cubic using 4 different geom line commands. I would much prefer that these values were all in the same column, and then there was a separate column over here that specified which model they belong to. So I'm going to do that. To do that, I'm going to pivot some data. So what I say is, let's load up the tidyr library. Let's create some tidy predicted data. I'm going to take that predicted data that has too many columns. I'm going to say I want to pivot longer columns 3 through 6, which are the predicted values, column 3, 4, 5, and 6. I want the names to go into a new column named model, the values to go to a new column named prediction. And then I'm going to say, let's mutate so that the model column is a factor where the levels of it are the same order as they are in our models vector. So this is just going to make sure that the models are in the order of intercept only, linear, quadratic, and cubic, so that our legend looks nice in a minute. If I look at my new data, my values of x and y are the same, but those 4 columns of predicted values have been brought down to be 1 column for the prediction and 1 column specifying which model that prediction belongs to. This is now a tidy or long data frame where I can say, like, give me a geom line where I do a separate line for each one of these, a separate prediction, you name it. So I alter my plot from before. I'm going to do something clever here, though. I'm going to say I want to start with a blank ggplot, and I'm not going to put any data in here. The reason for it is I want to plot 2 different data sets. This here is I want to do a geom point of the original data as a bunch of points. And then I want a geom line of my predicted data, where x is x, y is my prediction. We draw a line through it. OK? This is the result of doing that ggplot. We now have a plot that depicts the predictions for my intercept-only model, a horizontal line, my linear model, which is a straight line through the middle of these data, and then a quadratic line and a cubic line, which overlap one another, making basically the same prediction. Okay? So if we look at this, which one of these things looks like it fits the model or fits the data the best? Is it definitive? Any opinions? People too emotionally drained to talk? Been a long week? Cubic looks pretty good. I agree. The cubic and the quadratic are basically inseparable here. So this line here, you'll notice the color of it is about halfway in between quadratic and cubic because the line is the same line. So this is sort of one of the problems of visually comparing models. Right here, we know from the look of it that the cubic and the quadratic model probably both fit our data well. Parsimony would say, well, if they both fit our data basically the same, you might as well take the simpler model, but we might want some definitive way to determine which is the better model. The only thing we know for sure here is that the intercept only and the linear model are both doing a crap job. And in fact, the linear model is barely different from the intercept only model. When you have sort of parabolic data like this, it will look like there's no relationship between x and y unless you plot it and try something nonlinear. Okay. So what we might want to do, if you're in a case where it's a little harder to determine what is the best model for something, you might need some sort of metric that you can compare different models. Cross-validation is a widely used method for doing exactly that. Cross-validation is used to estimate how well models make predictions on data that were not used to fit the model. This is an important idea. If you want to know how well a model predicts something, you don't want to just have it predict the data used to fit the model, because overly complex models will do a really good job fitting to data that they see, but bad job doing fitting to like new stuff that comes in. This is essentially simulating what they call training and test data, sort of in the data science scheme. Cross-validation is a way to sort of generally apply it. Cross-validation is probably the best common way to evaluate how well general conventional models fit. And you can use cross-validation for any type of model that exists. Cross-validation is a general thing. You can always do it. It gets complicated for hierarchical data and longitudinal data, but there's ways to do it. Okay, so the idea behind cross-validation is this. You're going to split your data into K. K is just a number of folds, that is pieces. If you have 5-fold cross-validation, it means you took your data frame and split it into 5 different data frames. Okay? Then for each one of those folds, that is each one of your like sub data frames, what you're going to do is you're going to fit the model to all the data except the data in the fold you're on. If you're in fold 1, you're going to fit your model using folds 2 through 5. Then you're going to make predictions for the data that were omitted in the first fold. So you fit your model on 2 through 5, but you try and make predictions about fold 1. I'm going to draw some pictures of this in a minute if you think visually. Then what you do is you would calculate the mean squared error or some other measure of accuracy for all these predictions you made after running through all 5 folds. So if you have 5 folds, you're going to exclude one at a time each one of these folds and make a prediction. And at the end, you're going to look at your overall how good of a job you did predicting those across all 5 folds. Okay, and that's all you're going to do. A model that fits well in cross-validation will have a low mean squared error. Models that are either too simple for the data or too complex will give bad mean squared error. This is nice because it means it penalizes making models too complicated, but it also penalizes making models too simple. Cross-validation is that sort of just right sort of Goldilocks style of model fitting. Okay? So cross-validation is a good general approach to testing your models. So visually, this is what cross-validation looks like. So because this is a complicated thing, I tried to make some pretty pictures for it. So the idea is that your real data are over here, your real Y and X. This is an example of 5-fold cross-validation. So we've split our data into folds 1, 2, 3, 4, and 5. So for the first iteration of our cross-validation, what we're going to do is we're going to fit our model using these data. We're going to leave out fold 1. We fit a model here. But then what we do is we make predictions, but we use the X variables, the predictor variables in the fold we left out to make predictions. We put them here, over here, predicted values, and then we're going to compare these predictions to the real Y values. Then we're going to do this 5 times. You'll notice here I said pre-allocated space. On iteration 1, we're going to fill in this first space. And then these ones haven't been filled in yet. We're going to do this repeatedly so that we get to the last iteration. We will be fitting our model to the first 4 folds, predicting the predictions for fold 5 using the last rows over here. All of these will be filled in. And then we'll use all of these predicted values of Y, their differences between the predictions and the real values of Y to calculate our error. This is a complicated thing. And it's OK not to understand exactly what's going on here. But I keep it as an example, regardless of its complexity each year, because of the number of people who email me saying, thank you for your cross-validation code later on. I usually get about 5 to 10 a year who are like, thank you very much. Okay. Can you explain mean squared error using this picture? I kind of can. So these are predictions of Y here. Mean squared error would be equal to these predicted Ys minus the real Ys, each observation squared, and then all of those, the mean of them taken, if that makes sense. We'll see in examples here because we're going to run all this code. Okay, so what we want to do is we want to first pre-allocate this big data frame to store all the stuff in. So the idea here is I'm doing 10-fold cross-validation. So we're going to make a loop do this for us 10 times. So we need a data frame that will hold all of this, sample over things, filled up with stuff. So what I'm going to do is I want to figure out what rows go into which folds of my data by randomly sampling. You don't just want to take the rows in order in your data frame because the order of rows may actually matter in some way. You rather want to randomly draw. So what I'm going to do here is say, I want to run cross-validation with 10 folds. So I'm going to write this constant here, K, is just going to set in all the other things we run that we're doing 10 folds. I then say, I want to create a data frame out of my sim data, CV predictions. The idea here is I'm just going to copy my original data, to a new data frame and add some stuff to it. Then I say I want to create a new column called fold. This is just going to mark each row in our data set with a specific fold in our cross-validation. To do that, I'm going to say, let's sample from a vector of repeated numbers 1 through k, so 1 through 10, with a length equal to the number of CV predictions, that is the number of rows in our data set, with replacement equals false. What this means is every value of this repeated vector is going to be sampled exactly once and only once, which means the numbers 1 through 10 will be repeated 300 times, or up to a length of 300, and they'll be uniquely assigned to each row in our data. What this means is that exactly the numbers 1 through 10 will be assigned exactly 30 times each to each row of our, different rows in our data. So every fold will be exactly the same size and have their numbers assigned to them randomly. Then what I want to do is I want to create a bunch of empty columns, one column for each model we're going to run. So I use a shortcut trick that might be useful to you in the future. I say CV predictions. I subset down to a vector of names of the models here. I assign to it NA. This right here is a length 4 character vector. If you assign an NA to multiple columns in a data frame like this, it's going to create one column for each one of these names. So this line here creates 4 new columns in CV predictions, which are these: intercept only, linear, quadratic, and cubic. Because I'm going to run this code live, I'm going to copy this statement here, run all this. So k is equal to 10. CV predictions is equal to my original data. Sample all the folds. This is just going to go create a random number assigned to the fold. In this case, 746453. These are going to be the folds the data are pulled from. This here adds 4 columns to this, filled with NAs. The resulting thing is a big data frame where each element or each row of the data is assigned to a different fold, basically. And then we have a bunch of NAs, and we're going to fill them all in with predicted values. Okay. So now we're going to get into something ugly. So what I'm going to do here as an example is I'm going to show you how you can nest loops inside of each other. This is a very common programming thing when what you want to iterate over is not one vector, but maybe 2 vectors. So what we're going to do is we're going to loop over each model we have, and then within each model, we're going to loop over all of the different folds in our data to fit 10 models. So what this says is for mod in names models. This is the same thing we iterated over to fit the models. Mod is going to get replaced with intercept only, and then linear, then quadratic, then cubic. But then notice for each one of these models, well, that model is set to intercept only or whatever, we're going to run all this stuff a bunch of times. The model inside says for k in 1 to capital K. Capital K is the number 10, which means this loop in here is going to run 10 times, setting k to 1, then 2, then 3, then 4, then 5, then 6, then 7, then 8, then 9, then 10. Once it gets to 10, runs everything inside, the loop is going to go back up here, change the model to the next model, and then go back in here and run through k equals 1 through 10. This is a nested loop. So if you imagine in the very first iteration of this entire thing, k is going to be the number 1, and mod is going to be intercept only. So the code that's actually running is the fold rows are equal to CV predictions $fold equals 1. This is a logical vector that's going to be equal to true whenever the fold is fold 1. Then we're going to create a temporary model, which is equal to a linear regression. Same formula as before. It's going to go grab the model formula using intercept only. But now data is going to be equal to our CV predictions data, which is basically our original data, except it's going to subset only down to the rows, the fold rows, not fold rows. So this means exclude every row that's in the current fold. So for the first iteration, this says ignore every row where fold is equal to number 1. So this just deletes 10% of our data and runs this model. It runs the model, and then to our CV predictions data frame, for the rows corresponding to the current fold and the column corresponding to the current model, generate predicted values using this model specifically in the fold rows. So the model is fit using not the fold rows. The predictions are made using only the fold rows. This is complicated, but it's magical because it's doing a lot of stuff. So if there are 4 different models and there are 10 different folds, how many times is all this code running in here? I saw you, but I'm going to wait for somebody to type in chat or something. I need to solicit other people to be engaged. Exactly. It's going to run 40 times. Because what happens is for each model, the entire thing here runs 10 times. Then it goes back up and goes to the next model, runs it all 10 times, goes to the next model, runs it all 10 times. Right? This is pretty neat because we were doing a lot of operations with very little code. Right? It requires a lot of setup. Here's an excellent question. Is there a way to loop through 2 lists of things at the same time, like one loop that jumps forward 1 iteration in 2 lists at each time? Absolutely. You can do basically anything you want. You just have to figure out how to do sort of subsetting and things on the fly. But yeah, the way to do that would be to do something like for I in the length of the number of things you want to jump through, and then inside of it subset to the elements of the lists would probably be the easiest way. There's some other clever ways too. Okay, so I'm going to run this code, which due to the miracle of computing will run instantaneously. Okay, what we get in CV predictions is our original X, our Y, the given fold, and then predictions for every value of X using that particular fold. Okay, so now we have our predicted values. We're not done yet, though, because we got to calculate some other things. So what we want to know is we want to know which one of these models actually did the best. So what I'm going to do here is I'm going to use another loop to calculate the mean squared error. Okay, that is of these CV predictions. The squared error is just equal to the difference between the actual Y values and the predicted Y values squared. The mean squared error is taking all those values, the mean of them. So what I'm going to do is say my cross-validation mean squared error for each model, I'm going to say we set names. It's going to be a numeric vector of length equal to the number of models. It's going to be 4 models. Their names are going to be equal to the models. And then I run a quick loop that says, again, for a given model in the names of my models, it's going to run 4 times, replacing mod with intercept only, linear, quadratic, and cubic. The predicted squared error is equal to just the difference between the actual Y values and then the predicted Y values for that given model squared. So it runs this subtraction and then squares it. And then this right here, of course, is an entire vector of squared errors. I need to reduce this down to the mean of all these squared errors. So I say the cross-validation mean squared error for the current model is equal to the mean of that vector of squared errors. I run this whole loop here, and it's going to spit out my mean squared error for intercept only, linear, quadratic, and cubic. My intercept only's mean squared error and linear are basically the same. The quadratic and the cubic, in this case, actually did about the same. Normally, the cubic model, when I run this, is a little bit better than the quadratic. Okay? So it looks like in this case, it's not hurting us too much to use a cubic. All right? So based on this, you might not be able to tell the difference between quadratic and cubic. Generally in real data, if the real relationship is quadratic, the cubic will fit like garbage, but not in this case. So This provides you a toolkit that if you ever got to run cross-validation manually in the future, all these tools will work for you. You just got to swap the models that go into it. Okay. Any questions about that before I move on? That has ended the traumatic portion of today's lecture. It's all uphill or all downhill from here in a nice way. We can relax and cruise. Okay, good. And if anything else comes up, let me know. You want a 3-minute break? Well, the thing is we're going to be done in 15, and I want to cram through the last of these. Is that okay? Yeah, because we were going to be done in 15. Okay. Okay. The next thing I want to talk about is conditional flow. Conditional flow is a really important general programming thing, but it's really easy to understand. So I put it at the end of the lecture so that you've been traumatized. Now let's do something easier. Okay. So control flow or flow control is based on using if and else statements. You've seen the if-else function before in R. If-else is for doing a logical check on an entire vector and producing a vector of results. This is not what if and else are for. If and else are for checking a single value, a single true or false, and then doing something based on the true or the false. Here's an example of using it inside of a loop. I'm going to say for values of I in 1 through 10, if I modulo 2, this gets the remainder of dividing by 2. If this equals 0, that would mean the number is even. Print, paste together, the number I is even. Okay, if this is true, it does the thing in here. If this is not true, it goes to the next line. Else, if I divide by 3 has a remainder of 0, print I is divisible by 3. If that is false, else print the number I is not divisible by 2 or 3. Okay? If, else, if, else. You string them together like this. Running this loop generates this. The number 1 is not divisible by 2 or 3, but 2 is even, 3 is divisible by 3, 4 is even, 5 is not divisible by 2 or 3, 6 is even, so on and so forth. I have made R speak to me. Okay? So this is flow control. It's called flow control because you're controlling how values are flowing to different functions or different function calls inside of a larger structure. So for a value of I that's divisible by 2, the only code in this entire loop that runs is this. For something divisible by 3, it only runs this code. If something is divisible by neither 2 or 3, it only runs this code over here. So this is a way to selectively execute different parts of your code depending on values. This is very powerful, and it's actually the way basically everything in your computer operates and every function in R operates. If you provide an argument to R, an if statement activates when that argument is present and selectively executes code based on it. If you open up every function in R, they probably have an if and else statements looking for stuff. Okay. Your phone works like this. For instance, my phone, if I pick up my phone and I look at it, the screen turns on and shows my cat. That's basically an if statement saying if the facial recognition detects a person's face looking at it, wake up the screen. Computers are all if and else statements. All the stuff that's reactive, all that kind of stuff, it's if and else statements. These things are general to every programming language. Yeah. And it's actually a loop that's constantly checking for my face to appear too. It's a loop with an if and else statement, like everything else in every digital device that exists. Okay. So something that's nice about if statements is they're useful for handling special cases. If you have some loop that runs beautifully but breaks for exactly 1 or 2 things, you can just add if statements to catch these things and ignore them or do something different for them. If and else statements are also useful for producing error messages. For instance, it says if it detects a missing value, maybe print out there's a missing value here and there shouldn't be. It's good for catching things. And again, this is how all R functions that catch errors and things actually work. Some if statement catches the error and it spits out an error message. Okay. One common use for loops so getting back to loops quickly, is to load many, many files in one go. Maybe you have an entire directory of Excel files you want to combine into one data frame. Instead of manually loading them all and binding them together, we could just use a loop to do it. So let's say we have some folder filled with a whole bunch of CSV files. This is an example you can't run unless you've downloaded my class directory from GitHub or something, because I have a bunch of example data I created here. So let's say that you have a directory. In this case, it's called my example data directory for this lecture. And what I want to do is I want to combine all these Excel files. It's actually CSVs. I could get a list of the names of all the files in a directory using list.files, which if we haven't yet, we're going to use in a homework soon. I say list.files example data. These are the names of all the files in this example directory. What I want to do is loop over all these files and load them into R. Okay. So to do that, what I need to do is populate an empty list that is the same length as the number of files I have. We're going to write each file to a different element of the list. If there's 10 files, I need a length 10 list. So I say, I'm going to create a data list, which is vector of type list. Its length equals file list. That's 10. Okay. To give it nice names, what I do is I use stringer to remove the .csv from their file names. So I say, let's name them. The data names are going to be stringer package, string remove from that list of files, remove the .csv. I assign those names in, and now the data list's names are going to be this, which is the exact same as the file names, but with .csv cut off just because I didn't like the way it looked. Okay, we're going to use functions like stringer, string remove, a bunch more in 2 weeks. Next, what I want to do is I want to run a loop that will read in each data file and then write it to an element of data list. So I'm going to load in the reader library, and then I'm going to say for I in sequence along file list. Sequence along file list is just going to be a vector of the numbers 1 through 10 because there's 10 files. So this is going to say data list, data names I, so the name of the first file location in data list is going to subset down to the named element of this list. I want to assign to that the result of read CSV, pasting together the directory location and the file name of the files. So the first iteration is going to browse into example data and load that X example data CSV1. The second iteration is going to be the second file, then the third, the fourth, the fifth, the sixth, the seventh, the eighth, the ninth, the 10th. If I get head on the first element of this data list here, this would show me the first 3 observations of the data frame it read incorrectly. So my loop ran through and it read 10 different data frames in and assigned each of them to a different element of the list. Okay, but what I actually want is I want to combine all of these. Instead of a list with 10 data frames in it, I want one big data frame because all of these files contain the same type of data, so I can bind them together. If you're in a case like this, so I look at the first data frame, it has these column names, ID, X, and Z. This data frame, ID, X, and Z, they look like the same type of data. Let's combine them together. If every data frame in some list has the same columns in it, you can use dplyer's bind rows function to combine every data frame in the list into a single data frame. This is a really nice shortcut. So this says take the 10 data frames in data list, stack them on top of each other, and spit out a big data frame. So I do this as complete data. The resulting data frame is the 10,000 rows I'd randomly split among 10 different files, compressed together. So basically, this is a way in about 5, 6, 7 lines of code to read in 10 different CSV files and compress them into a single data frame. Okay? It's actually not very efficient, though. This is a lot of code to do some operation that's quite common. So there's other ways to do it, which I'll probably show here in a second. Before I do, I want to show you one other type of loop, while loops. While is a lesser used looping structure in R, but it's really useful in a couple cases. A common one is simulating data. Here's a quick example I'm going to show. So a while loop, rather than iterating over a predefined vector, the loop keeps going until some logical condition is no longer true. So this is the kind of thing that keeps running until it flips a switch off. An example of this might be, let's see how many times we need to flip a coin to get 4 heads. It's a common simulation game. What I'm going to do is I'm going to say the current number of heads is 0. The current number of flips is 0. While the number of heads we flipped is less than 4, keep running this code in here. This code says a single coin flip is going to be equal to a draw, random draw from a binomial distribution, 1 draw, a single coin flip, a coin flip being any probability 0.5 random draw. It's going to produce either a 1 or a 0. 1 is heads, tails is 0. If my coin flip is equal to 1, we're going to call that a heads. Take my number of heads, increase it 1. So it increments the number of heads. And then, no matter what, whether it's heads or tails, increase the number of flips by 1. It just keeps running this until the number of heads equals 4. In this time when I ran it, it took 6 flips of the coin to get 4 heads. It's a quick way to simulate coin flips. You could also do this for simulating dice or something like that. All sorts of different things you want to do. Simulation. While is a common use case for that. Technically speaking, all complicated regression models on your computer run on a while loop also that just says until it's reached either its iteration maximum or the gradient equals 0 or close to 0, keep running it. It's how optimizers work. So while loops are common, we just rarely write them ourselves. One time you might write a while loop is I write while loops when I'm scraping like data off of Twitter or something. I'll say like, well, the number of available draws from Twitter, because they cap how many you can do per hour. Well, this is like permitted, keep drawing, and then it will stop either if they tell me I don't have any left or otherwise keep running permanently. Anyway. Okay, one thing I want to talk about is vectorization. So let's say that we have a vector of numbers and we wanted to add 1 to each one of these numbers. In this case, I'm going to generate a length 100 million random normal vector. Okay, so let's say my vector has 100 million observations in it, and I want to add 1 to each observation. I could do this with a loop. Here I say my start time and my end time. Don't worry about this code. It's just here to display how long this loop took to run. I'm going to create a new vector filled with NAs of length 100 million. I'm then going to say for current position in 1 to 100 million, this vector's current value is equal to the old vector's current value plus 1. This is a really clunky way to add 1 to each element of my vector one at a time. Okay, this took about 4.79 seconds to run on my desktop computer. So adding 1 element at a time, 100 million times, took nearly 5 seconds. This is a really slow thing, and this loop is hideous. If you wanted to do addition, you wouldn't do it this way. It's slow, it's hard to write. Okay? We would instead probably just say, my new vector is equal to my vector plus 1. R here is going to take this length 100 million vector, increase this to be 1 repeated 100 million times using vector recycling, and then add them to each other, which took 0.28 seconds to do. This means when I last knit these slides, it was 27 times faster to do this than to do the loop, even though they were the exact same operation. The reason for this is doing it this way is optimized by R. It's not just easier code to write, it's straight up faster code to write. This is called a vectorized operation. It automatically did it the entire vector at once instead of element by element by element by element. Technically speaking, what it actually did is it called out to a library written in C, C++, or Fortran, depending on the computer you're on, and made it run a loop in the background. It's very fast. Okay. So the idea here is that anytime you can have a function do a repetitive operation for you instead of writing a loop, please do that. Loops suck. Writing loops sucks. As you saw earlier, they're traumatic to even explain and read about, so you should avoid writing them. There's all these beautiful functions in R that are vectorized and do these things for you, so you don't have to write loops. Examples of these are things like row sums, column sums, row means, column means. All these different functions are vectorized. They run over all the columns or rows in your data frames and stuff like that. So for instance, let's say we have a matrix and we want to get all of the sums of all the numeric rows. Instead of doing a loop to do it, I can just say, yo, give me the row sums of a matrix. And it gives me the row sums of a matrix. This beats a loop. Okay, this is way better. Okay, there's all sorts of these other functions. Cumulative sums, cumulative products, minimums, and maximums, right? If I have a vector 1 through 7 and I want its cumulative sum, don't do a loop that just keeps adding these things up to give you the cumulative sum. Just say, yo, give me the cumulative sum of 1 through 7 is 1, 3, 6, 10, 15, 21, 28. You don't have to do any pre-allocation. You don't have to worry about how to construct the loop. And it's probably 10 to 100 times faster. Okay, here's another one, position max, position minimum. This will take a matrix or set of vectors and it will output the minimum or maximum for each position in the vector or matrix. So if I say position maximum, I give it 3 different vectors. This will look in the first position of every vector and give you the highest value. So it's 2 because it's 0, 1, 2. It's also 2 because it's 2, 1, 2. 4, 1, 2, the third position, its highest value is 4. These are common things you might do with a loop, but are way better and easier to do in R using an existing function. Okay. So one other thing I want to show you that's way better to do vectorized instead of in a loop was that beautiful loop I showed you to load in a bunch of files. Okay. If you have a directory filled with tons and tons of CSV files, don't do that with a loop either. Use a vectorized data loading command. The Vroom package, which I think I've mentioned in lab, is a glorious package for really quickly loading in CSV, TSV files. Instead of looping over it, I can literally just say, I want to create a data frame of the result of Vroom vacuuming up an entire directory of files. I say I'd like you to Vroom the list of files in the example data directory. This basically says, give me all those file names with their file path attached. I don't have to say iterate over it. Vroom sees a directory filled with CSV files. It reads every one of them in and binds the results into one big data frame. Okay? If I glimpse at my data, it's the same thing I got earlier. This replaced that entire loop I did earlier with one line of code, and it actually did it like 30 times faster than the loop because Vroom is hella fast. If you got to load in a bunch of CSV files, do it this way. Vroom is quick. You can do this on your homework if you want, or you could use an lapply statement, which I'll show in lab. Okay. So that's the last thing I got. Your homework for the week is to do part 2 of the homework that I gave out last week. So just kind of finish up. We'll go over it in lab like usual. Same old. So yeah. Hit me up on Slack, hit me up on email. If you got any other questions, I am right here. And I will say, it's basically all downhill from here. The class gets continually easier and more fun from here on out. This is sort of the peak difficulty lecture. Next time, apply statements and writing functions, I'd say is a little bit easier. And from there, it's fun topics. Working with character data, drawing pretty maps, and then doing tables and model output. It's all easier from here.
Thanks, Chuck.
Absolutely.
Thanks. Have a good night.
Thank you.
Hi, Jack. I want to know how to do the appearance of our RStudio. Is that from global environment or?
To do what?
To do the, I think it's the appearance setting about the theme of the,
It's just here, global options, appearance here, and then these are all editor themes.
Okay.
So you can make it look like whatever you want here. I use, I like Twilight with the sky basic theme is usually what I do.
Okay.
It's pretty good looking. And I've also turned on an option, which if you downloaded the newest preview of RStudio, is code display rainbow parentheses, which I really like. And this makes the parentheses rainbow colored, which makes it a little easier to pick out which ones match to which ones. But that's in the preview version of RStudio if you want that.
Okay. Okay, thank you.
Okay, we got nothing else. I will hop off. Cool.